much.
Thank you. Thank you for inviting me and giving me the chance to present my work. As Lorenzo said, I'm coming from University of Oxford. Actually, it's just 1 year I moved there and in the process of establishing my lab. So what I will present today is more or less my journey up to here and my experience with developing tactile sensing technologies for robots. As you all know, so we are moving the use of robots from manufacturing environments, so where so there are well-defined tasks, though where we have in principle limited by behavioral diversity, there is no interaction with humans, to scenarios where instead we have unpredictable environments and robots need to be adaptable, flexible and have high behavior diversity and also perform safe human-robot interaction. In these new scenarios, we need to provide them with a sense of touch. Sense of touch in humans is really a relevant sensing system because it's used for assessing the object's material properties, weight, texture, shape. It is also used in grasping, manipulation, exploration, full body interaction, and also is different with respect to other sensing modalities because it's crucial also for motor behavior. And the interest and on tactile sense of touch has been demonstrated by more than 30 years of research in tactile sensing. You can find really huge amount of papers that develop new sensing technologies, but the majority of them were mostly demonstrators, so proof of concept. There were few integrated solutions, very few portable solutions. Most of the time they are developed for specific robots and so they are not portable on a different kind of robotic structure. The reason for this is because to scale up and start to think to a large-scale tactile sensing system needs to take in account a lot of requirements. So you can start to think about task-related requirements. So which is, so today we already asked this question, which is the best sensor or transducer to detect certain type of contact feature. So we need to decide, for example, if we need a sensor for a certain range of contact events, for sleep, for example, which is the static and dynamic range that is of interest for the sensor. We want maybe detect temperature. There are also other constraints that are related to when you think to have a system that is integrated to a robotic system. For example, we need to find out how to reduce the number of wires because we don't want to constrain the robot motion. We want in principle embedded without electronics. We want also to look at how our sensing system can well integrated with the existing hardware on the robot and also existing software to be able to close real-time control loop. And also there are other aspects related to manufacturability. We listen already today this kind of problem, maintenance, also the cost. Because we can, so you are thinking to cover a full body robot, the cost is an issue because you are thinking to produce like thousands of tactile sensing module, and all these requirements should be taken account and in the design of this kind of large area sensor we need to find a trade-off among them to achieve a larger tactile sensor system. And this has led to some example, but compared to the huge literature we have on tactile sensing, these are the more or less the example that we have since 90s. And you can see that the difference in numbers. And today I want to talk a little bit more in detail about this particular large area tactile sensor that has been developed during a European project called the RoboSkin. And I work on the development of this sensor and a further development of this starting from the RoboSkin. So RoboSkin Technologies in principle wanted to try to find a trade-off among several design requirements, and we thought that a good approach could be a modular system. So we design a flexible PCB with the shape of triangular modules that are interconnected. Why we decide this shape? Because if we took some hints from computer graphics, and usually you have that mesh are made by triangles. And we design this flexible PCB that could in principle conform through to 3D shape of the robot body, and is based on capacitive transduction principle. Again, why we decide to use capacitive transduction principle? Because the availability of commercial readout electronics. Everyone has a phone, so it's possible to find a chip that can help us in this sense, and that are cheap in principle. Each module has 12 capacitance tactile element that we call tactile. It's like pixel, but we use it the same word for tactile elements. And the chip actually can read up to, can provide up to 16 bits of resolution, but you have also to compensate about noise. So in principle, this version of the sensor could provide you 8 bits of pressure resolution. In this case, I'm considering static pressure resolution. Yes, sorry. So here you can see the chip that I was telling you before. This is a capacitor to digital converter from analog device, and this is like one of the tactile of the sensor. All over the flexible PCB there is a dielectric layer that provides compliance to the sensor and that deform under the application of a pressure on top of the sensor. And there is a conductive lycra that cover and act as a common ground plane for all the tactiles, and this provides the sensor the ability to detect contact with the non-conductive objects in principle. As I told you before, the triangles are interconnected, so you have a nice embedded network infrastructure, so the modules can talk each other, and they are connected to a microcontroller board through I2C buses, and the microcontroller board sends the tactile data to the PC. This is solve the issues of to have an embedded system that can be integrated in the robot body without constraining, without too much wiring, and also you can see the small dimension of the microcontroller board that performs some pre-processing on the tactile data that can actually install inside the cover of the robots. And one microcontroller board get data from up to 16 modules, and you have just one cable. So this allowed us to really actually integrate the sensor and pass the cable inside the robot body. The manufacturing of this system was also, so the integration also included some other steps. So in principle, what we did in order to integrate this system on different robotic platforms was to just design appropriate cover that could host the electronics on the back of the tactile modules, the triangular modules. We could just cut the PCB as we wanted in order to accommodate the covering for a certain shape of the robot body, and we could just glue it on the robot part, cover it with the dielectric layer and the conductive lycra, and we could cover in principle different type of robot body. You can see example of how the system was portable. So we could actually, we were not confined to specific robots for the covering. And you can also have an idea of how many tactiles you have on all this structure, because you don't forget that when it's a matter of scaling up, it's not just a hardware issue, it's also a software issue, because each tactile element provides you information, so you have to solve problem of handling a huge amount of data. This is quite relevant when you want to control system like this. So you have to collect all the data from all the sensor, process it, and send control action to the robot body. So it's different if you are dealing with 10 sensor or if you are dealing with 1,000 of sensor. This is just to show you the like some characterization that we did of this first development of the sensor. So you can see that up to 700 kilopascal, depending on which kind of probe we were using. So depending on which area of the contact probe we were using, you have a different kind of curve, but in this range we have a quite linear response of the sensor. And another interesting fact is this spatial response of the sensor. You can see that thanks to the dielectric layer, the response of each tactile element is overlapping, so this means that you can detect contact in principle between each tactile element. I forgot to say that in this version the spatial resolution, so the pitch from center to center of each tactile element was about 5 millimeters. And so we were looking, since a tactile sensor is a measurement system, we were starting to look at how we could work on, for example, the dielectric layer to change the sensitivity of the sensor and tailor it for specific application scenario. For example, we were looking at trying to increase sensitivity of the sensor for soft touch. Or for example, if you want to use it in different contexts where you're interested in more like manipulation task, you can also look at how change the dielectric properties of mechanical and dielectric properties of the dielectric layer to get a different type of sensor performance. And this is because if you look at the tactile response here, so you have that dielectric permittivity and also the ability to mechanical properties in principle can affect the tactile response. We have also another problem that was related to the sensor weight, because you are thinking if you think about it, we are covering a whole robot arm and we are maybe putting on 2 millimeters of dielectric layer, silicon rubber or whatever, and these affect the weight on the robot, and this also is to be taken in account when you look at control. So just I don't go too much into detail for time reason, but like we tried different type of elastomers and also fabric made covering for the sensor. We do characterization of the tactile sensor performances with all the different material that we tried for the electric layer, and we were also looking at another aspect that is important, is the aging effect. When you use silicone rubber, you have that the sensor can change its performances in terms of sensor sensitivity because of the aging of the dielectric layer. So if the dielectric layer change, you have different response. And this is also an issue because it means that you need to recalibrate again your sensor after a certain period. Looking also at, like, for example, how we could, instead to just like have a defined design for the sensor, we were also looking at how we can for example, have a tool to have a look at how we could, how the sensor works in different conditions and how we can change the geometry of the sensor, for example, and the dielectric layer properties in order to tailor the sensor for a specific application. So we developed a tool for that provide like a geometric parameterization, but also as a database of characterized dielectric materials. And we could, for example, select which were the contact pressure we were interested in, or like a contact area, and simulate the sensor behavior in that specific condition. And we could try, for example, you can decide that you don't need 5mm spatial resolution, so you can try to like change the geometry of the sensor to accommodate your requirement. This is also because, as we already said before, you have that we have a different spatial resolution in the hand or in the back. So, of course, for manufacturing reason, we design fixed shape triangular module, but for example, it could instead be wise to decide that for the back, that where we don't need high spatial resolution, we can design bigger triangular module or reduce the number of the tactile element, while we can instead increase the resolution in the hands. We also did, the simulator were also able to perform some multi-objective optimization and, for example, select the right dielectric material in order to get a certain required sensitivity, but also trying to not increase too much the weight of the sensor. This is just a validation that we did of the sensing result, of the simulation result with respect to experimental result. And of course there were some differences due to the fact that the characterized material, so like silicone rubber, differ from sample to sample, so you have a sort of variability in it. And I think that with this kind of solution, we were able more or less to fit some of the requirements. There are still some of them that are not achieved by our tactile sensor solution. For example, it is not multifunctional, so it doesn't provide only one type of transduction. And for example, capacitive sensor can detect up to 100 Hertz contact event. Of course, it's not able to detect vibration or like contact event that are goes at a higher frequency. It is a capacitive transduction method, also in principle detect only normal component of the force, so it's difficult, so it doesn't in principle provide you information about different force direction, is not stretchable, so you can conform it to 3D shape, but it is not possible to put it on the joint at the moment. So these were more or less, yeah, I put some in light green because, again, this is a suboptimal solution. For example, fit within available space. The shape is able to cover the majority of the robot body, but of course having fixed size triangular module means that sometimes you have to adapt, so maybe not all the robot cover can be covered completely. We also move further and we tried to solve some other issue, and we did a new run for the sensor. This in principle has been developed at University of Genova. In this one we had an additional tactile element between the triangular module to provide more coverage. We also changed a little bit the network structure, and in this version we are able to connect up to 64 modules to just one readout board. So, and also we used like one tactile capacitive element as a temperature sensor, because of course capacitive is also sensitive to temperature, so we wanted to use it for compensation. It's just an idea to show you yeah, like what happens. So this is a Shunk arm. We designed cover that change a little bit the shape of the robot, and you can see the patches of the skin in blue. And you can see that while my colleague is touching, you get dark dots that correspond to his fingers, and the dots get darker depending on the pressure that he is applying. Of course, again, you have a static resolution of 16 bit here. The problem is not just the hardware, so the problem of giving robot sense of touch. So as soon as you have the hardware, we need to also start to think about the problem of tactile perception, and so how the robot from all these tactile sensing data can infer what's happening on his body, and distinguish, for example, if he's touched by a human or he's touched by another object, and which kind of object is interacting with, and so on and so forth. So in this respect, what I was looking for was biological inspiration. So how is for biological organism sense of touch, including human, of course. And in this respect, I mean, if you look at like classical sense model plan act architecture, sensing is usually a passive collection of data that are used to fit a pre-structured model of the world. But if we look at instead a biological organism, including human, we can see that tactile perception is done through the body, so the body has a role, and also is not merely passive but is active. With respect to other also sensing modality, we touch the objects with our body. I just to provide you an example, if I can touch this table with my loose finger, I can feel the texture of it. If I stiff my finger, my joint, the information I have from this table is completely different. So it's not just by statically touching, but by actively interacting that we can get the most from our sensing system. And in order to go in this direction, I started to explore, for example, sensor morphology. And my question, so something that was at the very beginning in my head when I did like the work on dielectric material and trying to look at a simulator for the sensor, but here I was thinking like how the sensor morphology can effectively simplified and like first of all affect the tactile sensing readings and simplify a predefined, for example, classification problem. So what I did was just to put on my sensor a soft filter with different thickness, and just look at how, depending on the filter I have on my sensor, I could in principle be able to classify objects in different way. So what I did is to define object with some similarities, for example object with edge, with similar elongation, and I just start to like apply pressure on them, and I developed a unsupervised inference framework that was based on PCA and k-means clusterings. In principle, the sensor data, after I acquired them, are re-encoded in two axes of the biggest variance, and the k-means just create two different classes. And what I discovered that actually the sensor morphology as a role, so the fact that we have sensor and mechanoreceptor embedded in the skin, and there is the dermis that can deform in a certain way, is an important factor. And we discovered, for example, that if we get a 3 mm filter of the sensor, it was so we were able to just cluster together object with edges. So the edges becomes the feature with the most variance. While, for example, if we change just the filter, we were more keen to cluster together objects with the same elongation. So this to show that in the design of our sensor, we are to take in account like the compliance also of the body and the morphology. We did also another experiment by changing, for example, the number of sensor elements we were considering, and again this could change the accuracy of the clustering. I worked also in a project that is called Motion, where we were doing, we were trying to develop a robot that could perform palpation diagnosis. So, for example, detect different kind of cancer nodule and provide information about their depth in the robot body and their size. And in this respect, I started to look at the palpation task, and again. So here I was looking not just at the morphology of the sensor, but for example at the motion. So here I wanted to try to classify different kind of hard nodule embedded in a soft phantom. Sorry, I will come back to the previous slide. So we have different type of phantoms we developed to test our methods, and we were embedding several types. So in principle we have a small and deep nodule, big and shallow, small and shallow, and big and deep, and we place it in different position on the phantom. There were also positions that didn't have any inclusion. And again, we used our unsupervised framework this time to look at how different motion could affect our capabilities to could help us and simplify the classification task. And we were looking just by, for example, performing a rounding motion over each position, or just by going deep, and at which how much deep we had to go to. And you can see like the robot moving and the response of the tactile sensor there that related to what is doing. And on the basis of that, we train a supervector machine for classify different type of nodules. And we were able, with this framework, to actually select the best motion strategies that could maximize the accuracy of the right classification of different type of nodule in the different contexts, so changing, of course, the type of classes that you have. And finally, we don't have to forget that sense of touch is not just exteroceptive cutaneous sensing, is also kinesthetics sensing, and so the problem of proprioception also is important when we consider sense of touch. In this respect, I was working on like how to allow a soft robot to retrieve its posture, and I integrated one module of my sensor on the top of this soft robot that was like tendon driven. I just cut one triangular model on the like to get this hexagonal small piece of it. And so what we did was in principle to train a normal neural network to just have before the correlation between a camera and the robot posture, and also the robot posture and the tactile sensing data. And so here you can see, for example, the response of the sensor depending on the posture of the robots. And we were able, so you can see here is the posture based on the camera. This is the posture reconstructed from just the sensor, and we achieved quite a good accuracy in the reconstruction of the posture just based on the tactile sensor. In principle, my idea was that when the robots move, in principle is acting a pressure on the sensor. So from that response, I can retrieve the posture. And we had an error about 1 millimeter of the robot tip with respect to the real posture. And we wanted also, so in this case, when you have a soft robot, so it is compliant to external forces. So we wanted to like test these methods in situation in which the robot is actually moving not in free space but in a constrained space. So here you can see, for example, the plotted position of the and the factor, let me say, or like the most the tool center point of the robot. And here you can see that when the robot was able to move inside this constrained environment, we were able to retrieve his posture correctly. And also here, so we were able again to retrieve like the position of the robot in a correct way. So we were like actually show that it was enclosed as the wall in the space. And that's it, more or less. This is my journey on tactile sensing. I hope it was not too boring. And if you have any question, thank you so much.